Hi, I'm Gonzalo Tarvizol, secondary one for NS High School, right now here. Still going on with our Theoretical Mechanics Chapter 1, Kinematics. But for kinematics right now, in the past we have learned about those kinds of motions, and motions include straight line motions, projectile motion, and circular motion for those types. But what if we just group projectile motion and the circular motion together? So those two types of motion, when you group them together, well, you can call that curvilinear motion. This is the word curvilinear. So for curvilinear motion, it is way more wider than just projectile, wider than just circular motion, all those. It can consist of all different types of curves. So that's why you may find this curve, that word in front. So this is curvilinear. So you have many different types of curve. Projectile and circular motion is just a very special type of curvilinear motion. So for this type right now here, for this type over here, in this example, we're just going to use y being equal to fx, which is y is a function of x. Let's take a look at what do we have in this curve. You may find this circle over here. So from this circle that we have here, possibilities are when you draw the circle, you may touch the curve at one point, you may overlap with the curve at some point. But just beware, this circle and the curve that you have, when they overlap, they cannot make a space in between, in fact, closed space in between them. So from this part, all that we can have from this part is the circle. Well, if we touch it at one point, there is also a tangential that will touch at that point. Well, when you touch at one arc or overlap at one arc, you may have many tangentials from those. So that is this about the circle that you have here. Well, from this part, this curve from here, you may call it the curvature. That's what you may call it from this part, alright? Well, at the same time, curvilinear motion, you also may call that the planar motion. So these are two names that you may have for this curve over here. Well, right now, I'm going to prove one thing first. Wait, both of these are motions. Okay, so that's what you have. So right now here, because we're just starting on this, we need to get to know a few of those things that we may need to keep on using from this part. So that's why we need to prove them first. So after we prove, then we will know that they are right. Because if you don't prove it, whether it's right or wrong, you still may doubt that from the whole process, during the whole process. So first of all, let's prove. Let me see here. So from this part, just beware that this is not a K. This is from a Greek letter, and you pronounce it as kappa. But don't confuse this kappa with car park. You don't put cars inside here, right? So from this part, this kappa, you can call it that curvature. So it means the curvature. So this kappa, we need to prove that this is equal to. So here I need to change it to square bracket. So for this part is what we will need to prove first. But kappa, you may not know why is it first. So right now here, I'm just going to write that kappa is 1 over, well, this is not P also, this is rho. So kappa, this is 1 over rho. And rho is the radius that you have over here. So when you look at this form, you may think of like frequency looks like that, F equals 1 over lambda. You may think of that like we have learned it before during quantum chemistry, Rydberg's empirical formula. But just be aware now it is kappa equals 1 over rho. Alright, so this is that part. That means the only thing we have to find now is that rho. So we have to find what rho is. So it's this radius. So let's take a look. This radius, we take it from this circle that we have. Well, how about, let's think of what we can find using that circle. So if you want to find ds, it is r times the angle. So in this case, it becomes rho d theta. So that means rho, for this part, it is ds over d theta. Well, just let me tell you that here we got it from the definition of radian. So definition of radian, it goes like this. That means rho is just ds d theta. So this is that part, ds d theta. Is there anything else that we could find? Oh wait, you suddenly look at this graph, and then you find another theta over here. Are these two thetas the same? Well, let me tell you for now, they are the same. But then you may ask, like, how are they the same? So for this part, we're just going to take here, you have extended this tangential line, and then here it goes down, radius, perpendicular. So why don't we just take that as a rigid body? So you just take it as this part. Then you move it up. Then you can choose to draw that tangential too. But here, when you move an angle, let me say I also move the same angle since it is a rigid body. So if you move delta theta, you also move delta theta. And if you come down delta theta, you can also move delta theta. So that means that's how they are the same. Simple as that. So that means we could find something using theta. Or can we? So theta from this part, we take a look at what we can try to find. Well, theta. So let's think of, wait, how about rise in y over run in x? But beware, you also have inverse tangent for that. So rise in y and run in x. We can just straight away use y over x, but that's not good enough because you may understand it like from 0. So this, we don't want to use that. Then you may say, how about we use the increase? Well, let me tell you the best here is that since it's also saying about increase, you can just directly use dy dx, or you can just directly write it as inverse tangent y prime for short. So this is how you can write that. Then take a look at this part. Wait, you have this theta right in the denominator. What if we make a change like this? So here we're just making it into a reciprocal. D theta over ds. D theta over dx. From this part. Theta. Theta already had that. But wait. I'll make a change first. So here we're with y prime. So what if I make a change like this? That means first part, you need to differentiate theta with respect to y prime. Then you differentiate y prime with respect to s. So here you can call it as the chain rule for this part. So delta theta, d theta dy prime. So from that part, you just have to know the differentiation of inverse tangent. So that part will be 1 over 1 plus square of y prime. So this is part that you have. Then after that, dy prime over ds. Well, dy prime over ds, you cannot directly find it, as one is y, the other is an s. But let's just think about y. We're differentiating it with respect to what? Well, in this case, it is with respect to x. So this is what we'll have. So that means you differentiate this part with respect to x, and differentiate x with respect to s. So how about from this part we reciprocal at the same time? Here we also can find it, right? Y prime prime. Wait a moment, here we'll need to use square bracket. Okay, so this is the part that we have. ds and dx. What can we change for these parts? Or let's change any one. ds we refer back here. So ds is only for this part. But what if we use Pythagoras theorem to find it? So if you're thinking about using the Pythagoras theorem, well, you can try that out. And it'll become dx squared at dy squared. But wait, look at this. Would you have some confusion between them? Like, is it d then x squared, or is it dx then squared? So just to avoid that confusion, we put bracket and bracket for these parts. So this is how to avoid confusing d then x squared. Okay, then you will over. So from this part you will over, well, from parts still the same. Y prime prime. The next part is dx. So then next, we want to try to get rid of this dx over here. Since you can actually take this as dividing relationship, what if from this part, here you have dx then square. So when you take that out, you have a dx, since you also square roots that. That means what you have will be 1 at, so dy then, so actually it is dy square, then you divide dx square. That's what you actually have. Then you over y prime prime dx. So then dx and dx you are simplifying. Let me just extend this. Okay, so dx and dx both simplify. And then from this part, you can put both of them under the same square, but then you actually find that dy over dx has become y prime, then a square. Then beware, dx has been simplified. Then you take a look at this again. Inside bracket, inside square root, they have become the same thing. So since they're the same thing, then you can combine them together. Alright, so this is what you can have. So then, wait, we have only found for a row, but we want to show that it is kappa. So to show that, so this is just, if I write down the whole thing, it will become 1 over. So this is what happens if I write down the whole thing. So simply just need a reciprocal. And that's all you get. And so this, is it right? Yes, it is right. So here we have proven it. Okay, so we have proven this part is right. But just take note that in this part, kappa and rho, right now this part that what we have proven it is only like radius and the curvature. There is nothing to do about motion right now. You have nothing to do about speed, velocity, all those. It is only radius, curvature here. So this part is just the starting, so we're not combining it with that motion just yet. So in this lesson, I hope that you are clear so far. So I'm just going to end this lesson here. And if you like our videos, don't forget to subscribe to our channel. So we'll see you in the next lesson. Thank you for your watching.